السلام عليكم، نتمنى تكونوا بخير وعلى خير، ومرحبا بكم في هذا المقطع فيديو اللي غنتناولوا فيه واحد الدرس جديد في الفيزياء physics اللي هو oscillating systems. Oscillating systems are systems that undergo an oscillating motion. What is an oscillating motion? An oscillating motion is a back and forth motion around an equilibrium position. And we also define a free oscillating motion, which is an oscillation motion without an external energy input. So examples of these oscillating motions are examples of everyday life we find. So an example is the swing أرجوحة اللي كتعرفوا كلهم. Okay, so the swing performs a motion of back and forth between an equilibrium position. So if someone pushes the swing initially and then let it go, okay, ما يبقاش يتدخل فيها، ففي هذه الحالة هذه we call it a free oscillating motion، بمعنى ما كاينش شي واحد اللي غادي يعطينا an energy اللي غيزيدها لنا للسيستم. السيستم غيبقى يعني يقوم بديك الاوسيليشن by itself حتى يوقف إلا كان friction. داكشي اللي غادي نشوفوها بخير. okay. For example, we can find oscillators in watches. For example, this is a mechanical watch that uses here a quartz, I suppose, which is mechanical and electrical at the same time. It uses piezoelectric devices or materials. We have, for example, the old school clock with the hanging mass here. Okay, so this oscillation is used to measure time. We have also shock observers, which are also oscillators that are used as shock absorbing devices in cars and all sorts of vehicles. So of course there are many other examples of oscillating systems, but in this course we are going to focus on 4 of them. Okay, so the first one being the system solid spring, which is this one, which consists of a solid body of mass m suspended from a spring with non-contiguous terms. Okay, so this is an animation of the system. So this is the vertical system. We have also the case of the horizontal system, like this. Okay, and we have also the inclined case. Next we have the torsion pendulum. Okay, so it consists of a horizontal bar fixed at the end of a torsion wire. Okay, so we have an animation of this. So in this example we have a horizontal bar at which we have fixed some masses, okay, 2 masses, okay, and it performs this motion, this oscillating motion. It's like a rotation around this axis. Okay, so in this case, so imagine if there is a torsion wire. So this torsion wire it's like a wire that when it is deformed exerts a restoring force that wants to take or to get back to its original form. So when the system is twisted, when this torsion wire is twisted, this torsion wire applies a restoring force for this wire to get initially in the initial position. Okay, so this is what creates this oscillating motion. Okay, next we have the physical pendulum, which is any solid body of any form which is free to oscillate around a pivot, which is the axis of rotation, not passing through its center of gravity. So any solid object that is free to rotate around the pivot, and this pivot must not get or must not coincide with the center of gravity. Okay, any point other than the center of gravity, when it's a pivot, this system is called a physical pendulum, and of course it it makes this oscillation system in this manner. An example of it is what we have seen earlier. Okay, so as you have seen earlier, this clock. Okay, so this is a physical pendulum. Okay, so the pivot is somewhere around here, and it performs an oscillating motion, and we count these oscillations to measure time. Okay. And then lastly, we have the simple pendulum, which is a special case of the physical pendulum, where most of the mass is concentrated at the end of the pendulum. It is therefore a mass attached to the end of an inextensible wire, with negligible mass. So all the mass is concentrated at the end of the system, and this is called the simple pendulum. So an oscillating motion is characterized by one, its stable equilibrium position. Okay, so every oscillator has a stable equilibrium position، يعني البوزيشن اللي غادي يرجع لها او لا الى طلقناه وما كانش كيتحرك، هذيك هي البوزيشن ديالو ستيبل. اوكي، اللي كي الا حركناه منها، اوكي، الا بعدنا او لا يعني ازحناه من هذيك البوزيشن كيبغي يعاود يرجع لها. هذه هي الايكويليبريم، ستيبل ايكويليبريم موشن او لا position. Sorry. It is characterized also by the natural period T0, which is the time taken to make one oscillation, and its amplitude, okay, which is the maximum positive value of the quantity that expresses the offset x or the inclination theta from its equilibrium position. بمعنى it depends on the oscillator. So for example, the first one, the solid spring, we can track its motion using x, which is the distance, but for the remaining three, we track the motion of the system by an angle, which is the inclination. So both of them, x or theta, when we plot them with respect to time, we get this curve, which is a curve that's oscillating between two values, between a positive and a negative value. Okay, and from this curve we can figure out two characteristics. The first one is the amplitude, which is the value, the maximum positive value of x or theta, and T0, which is the time of one oscillation. Next, we have damping. So damping is caused by friction. So by moving a pendulum away from its equilibrium position and releasing it, the amplitude of the oscillations decreases until it cancels itself out. We say that the motion is damped, and the damping phenomenon is caused by friction. So due to friction, we notice that any oscillator after a while will be still، يعني غادي يوقف. اش كيعني هذا؟ كيعني بأن the amplitude of the oscillations decreases with time. غادي يبقاو غادي الامبليتود غيبقى غادي وكيتناقص مع الوقت حتى غادي يوقف. Why? Because there is friction. So depending on where there is friction or not, we have three regimes. So we have three regimes. We have the periodic regime, where there is no damping, so the amplitude remains constant, so no friction. We have the pseudo-periodic regime. So in this case, where the damping is low, the amplitude of the oscillations gradually decreases until it cancels itself out. So here we distinguish between two types of pseudoperiodic regimes. So the first one is caused by fluid friction, where the amplitude decreases exponentially, and solid friction, where the amplitude decreases linearly. So an example of fluid friction is friction with air, which is a gas, or friction with water, for example, some kind of fluid or liquid, which is also fluid. An example of solid friction is friction with an object over a surface, for example, as we can see here. So we can imagine that there can be a friction between this mass and the plane, which is solid friction. The last regime is the aperiodic regime or the non-periodic regime. So in this case, where the friction is significant, because no oscillation occurs. And according to the importance of the damping, we distinguish between three regimes. The undercritical regime, the critical regime, and the overcritical regime, which are depicted in this graph. So where friction بزاف, the amount of friction is significant, the system doesn't even oscillate. بمعنى the amplitude decreases until it gets to zero without even making an oscillation. Okay, so this is called the aperiodic regime. So we move now to section 2, study of oscillating systems. And we are going to begin with the oscillating system solid spring. So in this case, we are going to study the horizontal case, the horizontal system solid spring. And to study its motion, first we need to figure out the differential equation of motion. So for that, since we are going to use Newton's second law, we need to follow the 5 steps we have seen. So the first step is the study system. So in this case, we are going to study the object C. The study system will be object C. So we're here, position 0 is the equilibrium position. So the second step is forces. So object C, like here, okay, is subject to its weight, it's subject to R, the reaction of the plane, and to the tension of the spring, which is the force, the restoring force of the spring. So notice that the direction of T is always towards the equilibrium position, which is position O. Okay, so this force tends to make object C go back to its initial position, or the equilibrium position. So the expression of T, is equal to minus kx times I, which is the unit vector of the axis. So notice there is a minus sign. There is always a minus sign here. Why? Because if x is positive, it means that T should be in this direction, which is in the opposite direction of that of I. Sign minus. Okay. So we study the motion of the system in a frame of reference assumed Galilean, and we locate the center of gravity of object C using the OX axis. Okay. So by applying NSL on object C, so sum of forces is equal to the mass times the acceleration. This means that P plus R plus C is equal to mAg. By projecting this equation onto the OX axis, we find, so P is 0, the projection of R is 0 on OX. T, so we replace T with minus kx, okay, is equal to minus, to m_ax. And since the motion is along the x-axis, ax is equal to a. And we remind you that a is the second derivative of x with respect to time, which is equal to x2 dots. We can represent this, the second derivative, by x2 dots, so that the equation is lighter. Okay, so we replace it here, and then rearranging, كنحصلوا على a differential equation, which is the differential equation of motion of x of t. x2 dots plus k over m times x is equal to 0. هنايا k باش نذكركم k is the spring constant. نذكركم بها k is the spring constant. Units ديالها is Newton per meter. Remark: the same equation is found for the inclined and the vertical case of the elastic pendulum. Okay, so we are going to see these cases in applications later on. Now let's continue. So the solution of this differential equation is in the form of a sine equation or a sine function, which is x of t is equal to xm. Xm is the amplitude, okay, times cosine of 2 pi over t0, which is a natural period, times t, plus phi, which is the phase at t equals 0. Okay, and here are the units. So x and xm are in meters, t0 is in seconds, and phi is in radians. And x of t is the elongation, okay, in general. So how to find out the expression of t0? So you should be able to demonstrate how to get to the expression of t0. So to get there, we need to derive twice the solution, x of t. So we derive it the first time, we get this equation. By deriving it twice, we get this equation. And here we notice that this xm times cosine is x of t. Okay, so it's minus 2 pi over t0 square times x of t. So we replace the expression of x2 dots and we replace the expression of x2 dots in the differential equation in here, what we have found here. So it's this minus 2 pi over t0 square times x plus k over m times x is equal to 0. We factorize by x, so we have a product of two terms is equal to 0. So mathematically, one of them should be equal to 0. Since we know that x is not equal to 0 all the time, meaning that this term should be the one that's equal to 0. And putting this equal to 0 gives me the expression of t0, which is 2 pi times the square root of m over k. We have also the natural frequency, omega 0, which is linked to t0 by this equation. Omega 0 is equal to 2 pi over t0. Replacing t0, it's this expression. We found out that omega 0 is equal to square root of k over m. And the unit for omega 0 is radians per second. Okay. Small remark: we can replace in the differential equation k over m with omega 0 square, which is equal to k over m. Second remark: so this has to do with the equation as you have seen in tronc commun. So as you have seen tronc commun, t is equal to k, the spring constant, times the absolute value of delta L, which is the elongation. So delta L is L, the length of the spring at a certain position, minus L0, which is the initial length of the spring, or let's say the rest or the length of the spring at rest. So let's imagine that we have a spring. Its natural length or its length at rest is L0. So suppose we attach an object and we elongate the spring. So the length now is L, bigger than L0. So delta L is the difference between L and L0. So the bigger the difference, the bigger the force. Okay. So if we choose the origin of the axis x, OX, to coincide with the length or the equilibrium position, then this elongation delta L will coincide with x, okay, the position of the objects. That's why delta L is equal to x. So t is equal to minus kx times the unit vector I. And notice here that we have also added this minus sign, so that t is always in the opposite direction of I if x is positive, and if x is negative, t will be in the same direction of I, okay, as you have seen here. So if we have x positive, meaning that the object is here, okay, so t is in this direction, so opposite of that of I. That's why you have a minus sign. So let's see the other case where x is negative, meaning that the object is in the other side, meaning that the spring is compressed. In this case, the spring will apply a force T in this direction. T will have the same direction as I. Therefore, since x is negative, negative with negative cancel each other, and we get a positive value here, meaning that T is in the same direction of I. Okay. The third remark is that the more general equation of the spring tension is T is equal to minus k times not x but x minus x0, where x0 is the x component or the x coordinates of the equilibrium position. هنا في الحالة العادية في أغلب الحالات x0 is equal to 0, بمعنى the equilibrium position and the x coincide with the origin of the axis. ولكن إذا ما كانت القضية هذه, you should know that we should replace x with x minus x0. Okay. ولكن في أغلب الحالات كتكون x0 is equal to 0. Okay, so we are going to see two applications of this spring constant. Okay.